Hello, this is Hossein Haddad Kulu, postdoc researcher, and our presentation is about our project, Alternative Cementitious Material, ACMs for Durable and Sustainable Transportation Infrastructures. Former PI of this project was Professor Varda Ashraf. Former students was Rakib. Current PI is Professor Landis. And I am Hossein working on this project. What's the problem? The problem is that state duties spent as high as $100 million for winter maintenance of roads. Duty issues are de-icing chemicals, freeze-thaw cycles, cracking that results in spalling, scaling, and corrosion. You can see the pictures here. We think that there is a potential for reducing the maintenance cost using ACMs, because ACMs are usually byproducts of other industries and cheaper than cement. Objectives of these projects are optimizing and developing ACM concrete for formulation, finding a formulation for CO2 activated concrete, measuring the durability performance of this concrete, and measuring the service life, predicting the service life, and calculating the life cycle cost of this concrete. First of all, let's talk about hydration. In hydration, we know that C3S and C2S react with water, and we will have CSH and calcium hydroxide. CSH is binder and we love it, but calcium hydroxide is byproduct. And here we suggest two solutions for consuming this extra calcium hydroxide. First, using pozzolanic reaction with siliceous material or aluminum siliceous material, we can react with this CS and produce some extra CSH that is binder, and we like it. Again, the next solution, second solution, is using carbonation. In carbonation, we use this CH, we inject some carbon dioxide, and this CO2 reacts with CS, CH, and the result is calcium carbonate. Both of these pozzolanic reaction and carbonation decrease the porosity and increase the density, and we will have a denser microstructure. It means that help to increase durability. Here is a picture that we can compare Portland cement concrete system versus Portland slag cement concrete system. At the left, you can see that here only we have cement grains and hydration, but here we have cement grain and some slags. The slags will have some pozzolanic reaction and result in better and denser microstructure. We know that pozzolanic reaction is much slower than hydration, longer setting time, less amount of C3S and C2S. It means less heat of hydration and less thermal cracking. Also, we know that using pozzolanic reaction, in this case a slag, we will have denser microstructure. Materials and mixtures in this test are OPC, type 1-2, slag grade 120, 38% sand, 62% gravel. Our binder content is 600 kilogram per cubic meter. Water cement ratio is 40%. And we have 6 different batches with different slag replacement starting from 0 to 100%. Here we have 3 tests. in this presentation a slump test, compressive strength 4x8 cylinder at 3 different ages, 3, 7, and 28 days, and RCPT test as an index for durability. This is a picture for our hydration process, and this is a picture for our carbonation curing that we use carbonation chamber for curing the cylinders. We have a 3 curing procedure: hydration, 4 weeks in moist room, hydration plus carbonation, 3 days in moist room, 4 days carbonation chamber, and 3 weeks in moist room, carbonation plus hydration, 1 week in carbonation chamber, and then 3 weeks in moist room. So totally we have 3 curing procedure. Slumps. You can see that by increasing the slag content, first at low dosages, 20%, we will have an increase in the slump, but after that, we have decrease in slump values. It means decrease in workability. About compressive strength, this is the results for hydration curing for different aids. You can see that by increasing slag content, here we have decrease in compressive strength at early age, 3 days, because we said that pozzolanic reaction are slower than hydration at early age, but after 4 weeks, we have some increase in compressive strength, and optimum is 45% for hydration curing. For hydration carbonation curing, again, the same trend at early age. It can be seen that there is a decrease in compressive strength, but after 4 weeks, we have some increase. And here the optimum is 65%. The next slide shows the compressive strength result for carbonation hydration curing procedure. Again, decrease in early age and some improvement at later age. Here, 20%, 45%, 65%, all of them have good results. The next slide shows the same results for compressive strength in another way. Here we compare the results with reference line, which is compressive strength for 4x8 cylinder for control batch. It means 0 slag, 100% cement, and only hydration. It means no carbonation. The black line shows hydration, red line shows hydration plus carbonation, blue line shows carbonation plus hydration. Here, after 3 days, we can see some improvement at carbonation plus hydration at 20%, but after that, we see decrease in comparison with the control batch. But after 7 days, here we can see some improvement at carbonation hydration, blue line, until 60%. After that, we see decrease. The same, almost the same for hydration carbonation. The red line, we can see some improvement until 60% and then decrease. For after 4 weeks, 28 days, we can see some great improvement. For example, about 30% improvement for the red line, which is hydration carbonation. Also, we can see some improvement in carbonation hydration until 60%, but 65%. But after that, we see a decrease in the results of compressive strength. Here, we'll show rapid chloride permeability test, RCPT. In this test, we will show charge passed in for a specimen versus slag content. Here is for hydration, and it can be seen that in hydration curing, by adding slag content, we'll see decrease in charge passed in our cylinder, which means better, actually less permeability or better durability. The next one shows hydration carbonation. Again, by increasing slag content, we can see improvement in permeability from, for example, moderate to very low permeability, which is good for durability. For carbonation hydration curing procedure, again, it can be decreased strength, but here we see some increase in charge passed in our cylinder, and here we need to study more. But the trends for all of them is decreasing. It means adding more slag means more positive reaction and less permeability. So the results shows that higher slag content lowers the workability. Slag improved compressive strength at later age. 65% slag is the optimum for compressive strength. Carbonation hydration improves compressive strength at early age. Hydration plus carbonation curing procedure results in better strength at later age. Higher slag content lowers the chloride penetration, and hydration plus carbonation promotes the chloride penetration resistance based on our CPT test. So let's talk about the significance of results. Here we have a which shows the CO2 injection into a mixer. Here, see here in a real mixer. So using CO2 injection, we can have clean concrete. Using this method, we can improve durability because we have a denser microstructure. It enhances compressive strength. It reduces carbon footprint because actually we are consuming CO2, carbon dioxide. Potential applications could be in precast concrete, in ready mixed concrete, and in masonry. Future work will be studying shrinkage behavior of these concretes improved with slag and CO2. Studying durability performance, it means, for example, we are planning to measure bulk and surface electrical resistivity of our specimen, and then calculating the formation factor as an index for durability. Also, we are planning to predict the service life of our structures using this concrete, and analyzing the life cycle cost of structure made with these concrete. I would like to thank TIDC for funding. Also, I would like to thank University of Maine, Professor Landis, Professor Ashraf, Rakib, and Concrete Lab. Thank you very much for your attention and any questions. Thank you.